Today will look at the first lecture of chapter number 8, and this chapter basically deals with momentum, impulse, and collisions. The learning goals for today's lecture: the first one, understand the meaning of the momentum of a particle and how an impulse causes it to change. The second, identify another form of Newton's second law. Third, learn the conditions under which the total momentum of a system is conserved or constant. And finally, comprehend and use the conservation of momentum to solve the problems involving collisions. These are the goals of our lecture. As an introductory slide here, you have a truck that's about to collide with a small car, and we want to know what happens after the collision. So we say here which way the wreckage moves after the collision, or how would we decide if we have billiard balls and you knock them and they go into different direction. And we say here, we cannot use Newton's second law to solve such problems because we know very little about the complicated forces involved in situations like this. To solve such problem, we introduce momentum, impulse, and conservation of momentum. So this is basically here the motivation why we deal with momentum in situations like this, where really the forces are going to be complicated. So it's best to deal with momentum. Now, what is our definition for momentum and impulse? Now, the definition for momentum of a particle is the product of mass and its velocity. So that's by definition here, P, and we're going to use a symbol P for momentum. And it is the product of mass and velocity. Remember, in chapter number 6, we dealt with kinetic energy, and we said that kinetic energy is equal to 1/2 mv squared. So it's a product of mass and speed. Or in this case, no, we're talking about a vector quantity because the velocity here is a vector quantity. Now, if you look at our figure here, this is the x-axis, that's the y-axis. We have a particle of mass m moving with velocity v, and there is a green arrow here to indicate the magnitude of our velocity. And then we have here a blue curve which is longer, and the reason for that, it is because you're multiplying your velocity with the mass, and the mass here is a scalar, and it's going to make your vector or the magnitude of your vector bigger. And that's why we have it here as mv squared. So if you just want to look at this figure and how to read these notations here, or how these vectors, why the blue vector is bigger than the green vector, that's what it means. And that's by definition is the momentum is equal to mv, and it's a vector quantity because the velocity is a vector. Now, what are the SI units of this? Well, the units of mass is kilogram. The units of velocity is meter per second. So the units here are kilogram meter per second. Now remember, when we talked about force, we said it's MA, and the units of mass was kilograms, the units of A was meters per second squared. So it's kilogram meter per second squared, but we named that Newton to honor in Newton. And the same thing done, we did the same thing when we talked about work or kinetic energy or potential energy or energy in general. We named the unit after joule. Well, in the case of momentum here, the unit stays in SI units, and it's not named after any scientist. It's just kilogram meter per second. So that's one of the units basically that it's not named after a scientist or to honor a certain scientist. Now, if you look at what we did in chapter number 4 and 5, when we talked about Newton's second law, and we said basically the summation of the force or the net force should equal to MA. And if you know from what we did in chapter number 2 and 3, we said that A basically it's dV by dt. And we defined momentum here as mv, where m here is a constant quantity. So if I look at momentum here, which is equal to mv, and I take dp by dt, since m is constant, it will stay as it is, and you will have here a dv by dt. So actually, m dv by dt should equal to the summation of the force. And that's why we can write Newton's second law as dp by dt if our mass is constant. It's not changing. You may have situation where the mass changes as a function of time. But if the mass is constant and doesn't change with time, so it's only your velocity, in that case, we can write Newton's second law as dp by dt. So we define what momentum is, and we define in Newton's, or we can write in Newton's second law for a constant mass as dp by dt. So these are the two concepts, or one of the concept that we're going to use today. Now we're going to look at impulse and what we mean by impulse. You look at the figure here, you have a tennis ball, it hits a racket. As soon as it gets to the racket, it will deform it, and it will stay with it for some time, and then it recoils back. So it will stay for a certain period of time, and then it recoils back. Well, we say that the force with which the ball hits the racket on the racket itself, or the net here, it will basically start causing a force on it, and then the racket will slow it down, and then it will push it back. And in this case, okay, the racket has caused the ball to recoil back. So during that time interval, what is the force on this tennis ball? So if you basically take a plot here with the net force as a function of time, you may actually find that you may get a curve like this, the red curve here, where that's how the force will basically, we're talking here about, you may think about it differently here. I will think of the force on the ball caused by the racket. And the force will be when, actually, it will be maximum when the racket is stretched to the maximum and it recoils back. And that's why you get a curve like this, a bell-shaped curve here. Now, we define an impulse as the product of the force and the time interval during which it acts on the particle. And we give it a symbol J, and we consider it as a vector. So if you want to get the product of two things, it's equivalent to taking an area. If you get a curve like this, where on the x-axis you have t, and in the y-axis here you have force. So it's the product of these two. It's like the area under this curve here. And if you want to get the area under this curve, you actually have to do it by integration. So J vector here will equal to the integral from T1 to T2, the summation of the force, delta T. Now, if you have a constant force, then it will be constant over the whole time interval, and the area will be easy. You just take the area of the interval of the rectangular here, which will be the summation of the force multiplied by delta T if your force here is constant, or if you take an average force. Sometimes it's not easy to measure the force as a function of time, but if you know later on we'll explain when we look at change in momentum, you may actually get the average force. And if you just take an average force, you multiply that by the time, it will also give you the impulse as well. So the definition of impulse here, it is the force exerted on the particle during the time that this force basically affecting the particle. So we look at the product of this. And that's another definition today that we use for impulse. Is this clear? So now, if I want to look at the relation between impulse and momentum, as we say here, impulse momentum theorem. So we define our impulse as the integral from T1 to T2, the summation of the force, delta T. But remember, in the previous slide, we said that the summation of the force should equal to dP by dt. So it is the integral from T1 to T2, where for the force, it's dP by dt times dt. So you can cancel the dt with the dt, and you get dP here. Of course, you're going to change the limits of your integral from T1 to T2 to P1 to P2. And you know that the P is a vector because your force is a vector here. So now, if you integrate this, it will give you P, and you have to integrate this from P1 to P2. And this, of course, will give you P2 minus P1. And that, of course, is going to equal to the change in momentum. So the impulse here, which we define as the product of the force on the particle over the time interval where the force is exerted on the particle, equals to the change in the momentum of the particle, meaning the initial momentum when the particle gets in contact and the final momentum when the particle gets out of the contact. So here the impulse can be regarded as the change in momentum, which is P2 minus P1. And this is the relation now between momentum and impulse. So we defined momentum as mass multiplied by velocity. We defined impulse as the integral of the force delta T, and you go from T1 to T2, or we said also you can write it in terms of the summation of the force multiplied by delta T if your force is constant or if you take an average force. And here we define that the impulse should equal to the change in momentum, which is P2 minus P1. Are these concepts clear? Any questions on these? Now, we in chapter 1, in chapter 2 and 3, we talked about kinematics, and we started from position to displacement to velocity, to acceleration. So we were only looking at describing the motion. We did not look at the mass. We did not consider the mass. In chapter 4 and 5, we tried to pay attention to where we get the acceleration. And when we used Newton's laws of motion, the second law related the acceleration to the mass. So the acceleration basically is affected by the mass of the particle. In chapter 6, we introduced a quantity where it's the kinetic energy, and we said this is equal to 1/2 mv squared. So we have a quantity that contains both now, the mass and the speed. Here we're going to include the mass and velocity. We're relating the mass with velocity as well. And we told you that you can write in Newton's second law in terms of this quantity, which we call momentum. So how are we going to look at these two quantities, which relate mass and velocity? One is a scalar, which is the kinetic energy, and one is a vector, which is momentum. Now, you look at the situation that we have here. We have a baseball player. He wants to throw a baseball. Well, when the baseball leaves his hand, it must have a speed. So he has to do work to give it that speed. And you know that when we talked about work, we said that the total work should equal to the change in kinetic energy. It should equal to K2 minus K1. So when he starts from this point here, the K1 is going to equal to 0. And when the ball leaves his hand, it will have some speed or velocity, and that's where the kinetic energy comes in. So now he has to do work to bring the ball to this level here. To this point here, where it will leave his hand. Now, this will be a displacement S over time interval delta t. Now, you know that the work done should equal to F dot S. And this should equal to the change in kinetic energy. So the work that done over this displacement here will give you the kinetic energy gained. Whereas if we look at the time interval, that will be the momentum gained. Remember, we said that J should equal to the change in momentum. And the change in momentum is equal to P2 minus P1. But since he's starting from V is equal to 0, so that will equal to 0. So the change in momentum here will give you what? Will give you the momentum that it's gained by the ball. So from this cartoon here, we say changes in momentum depends on the time over which the net force acts, and it's a vector quantity. And changes in kinetic energy depends on the distance over which the net force acts, and it is a scalar quantity. Even though these two, kinetic and momentum, relate mass and velocity, but actually momentum as a result of the net force acting over delta t, and the kinetic energy gain comes as a result, or the change in the kinetic energy comes as a result of the net force acting A over displacement delta S. So that's the difference or the comparison between the two. Is this clear? Let's take an example here. And this example here, we're going to look at momentum versus kinetic energy. You have considered two identical ice boats, mass m and 2m. The wind exerts the same force So it is the same force exerted on both of them. The boat starts from rest and across the finish line a distance s away. Which boat crosses the finish line with greater kinetic energy, greater momentum? Now, if you look at the two boats here, they have the same sail. And if you look at the force, they give you the same vector, red vector here, with the same magnitude. That means the force is the same on both of them. But this one is mass m, and this one basically mass 2m. And that's the finish line here. So you can ask which one will reach the finish line first, which one will have higher velocity, and so on. We can argue using what we learned in chapter number 4 and 5 and 2 and 3. You know that in chapter number 2, we can consider this as one-dimensional motion. We can say that the Vx should equal to the V0x plus AX t. They're starting from rest, so this will be 0 here. So you can say that the Vx of the m boat, the boat with mass m, should equal to the acceleration of boat with the m times t, and Vx of the 2m should equal to the acceleration x of the 2m times t. Now, if you consider Newton's second law, where you say that the force should equal to ma, and in this case we'll consider the x component, so the fx is equal to max, and you only have the same force. So f here, which is fx, or the magnitude of the force that you have, should equal to max. So ax here will equal to f over m. So axm should equal to f over m, and ax2m should equal to f over 2m. So you know that the acceleration for the second boat, or the boat with the 2m, is going to be smaller. So you know right away that they are not going to get to the finish line at the same time. You know that the smaller one probably will take less time to get there. So let's look at that from consideration of work done. And we say that the work done should equal to F dot S. And in your case, this will equal to Fs, because the angle between the force and displacement will be 0, and cosine 0 is equal to 1, and you take the magnitude. That will equal to the change in kinetic energy, which is kinetic 1 minus kinetic 2 minus kinetic 1, but kinetic 1 is equal to 0. Because you're starting from rest. So if I look at the work done on the boat with mass 2m, this should equal to Fs, because it's F dot S. It would be kinetic 2 minus 0, and it should equal to kinetic 2 here, because kinetic 1 is equal to 0. So for the one with mass m, it will be the kinetic 2, and the kinetic energy, which is K2 in both these cases, is going to be the same. It's not going to be different, because it is the magnitude of the force is the same for both of them. The magnitude of the displacement is the same for both of them. And K1 for both of them is 0, because they're starting from rest. So K2 is going to be the same. So you can say here that they will actually reach the finish line with the same kinetic energy. But you know that kinetic energy is equal to 1/2 mv squared. So you know right away that the one with the 2 mass, it will have a lower speed when it gets to the finish line. And if it has a lower speed, that means, and you look at the acceleration, it will have a longer time as well to get there. If I want to look at change in momentum, and we already discussed that, we said that change in momentum should equal to the impulse, and the impulse is going to equal to force multiplied by delta t if we consider the force constant. In this case, it's a constant force. So the change in momentum will equal to F delta t. We'll use m here for the boat with 1 mass. We'll use 2m for the boat with the 2 mass, but we know the one with the 2 mass will be slower, meaning the time taken by the boat with 2m will be greater than the time with the boat that has 1m. That means the 1m will reach the finish line first. And that doesn't, in part A, we said they reach the finish line with the same kinetic energy, but they don't reach at the same time. So now your momentum of the boat with the 2m will be greater than the momentum of the one with 1m. So even though, that's the idea here, even though both these quantities involve mass and velocity, in the case of kinetic, it's v squared. That means you're getting a scalar quantity. In the case of momentum, it is v, where you're getting a vector quantity. And this is basically the difference now. Is this clear here? Any question on this? Now, let's deal with another example here, a ball hitting a wall. So you have here a 0.4 kilogram ball. You throw a 0.4 kilogram ball against the wall. It hits the wall moving horizontally to the left at 30 meters per second. It rebounds horizontally to the right at 20 meters per second. And they ask you here, find the impulse of the net force on the ball during the collision with the wall. And then if the ball is in contact with the wall for a 0.01 second, find the average force that the wall exerts on the ball during the impact. Now, the mass of the ball is 0.4 kilograms. Now, you know that momentum, it is mv. But since I'm dealing with left and right here, so it's only x component, so I'm going to deal with px, which should equal to mvx. So I'm not dealing with the whole vector, I'm dealing only with the x component of the vector. Now, before I will call it 1, and after I call it 2, which is, it could be initial and final. So I told you in this book, we always use 1 and 2. So before the collision, your ball is moving to the left, which is along the negative x direction, and that's why we say that v1x here will equal to minus 30 meters per second. And after the collision, it moves to the right, and that's why we say v2 now, x is equal to 20 meters per second. So your v1x here is equal to minus 30 meters per second. The v2x here will equal 20 meters per second. Now the impulse, and remember, the impulse is a vector as well, and it's equal to the integral, or you can say it's just equal to the summation of the force delta t if the force is constant. So the impulse is a vector as well, but I take the x component only in this case. So jx will equal to the difference, which call it delta px here, which is px2 minus p1x. And p2x is mv2x, and p1x is mv1x. So it's mv2x minus mv1x. you can take the m as a common factor, so it will be v2x minus v1x. The v2x is equal to 20, it's positive quantity here. The v1x is negative quantity, but you have a negative here, so 20 minus 30, that's 50, so you get 0.4 times 50, and that gives you 20 kilogram meter per second. This is your impulse now. Now, in part B, they ask about the average force. And we already defined that your impulse should equal to the average force, delta t. So in this case, if I only just take the x component, it will be the fx delta t. So your fx here, which is the force exerted by the wall on the ball during that time, it will be delta px over delta t, which is 20 over 0.1, and that gives you 2,000 in newtons. And now this is the average force exerted by the wall on the ball. You may argue about this, and recall if I told you that the ball hits the wall. Why? I told you by Newton's third law, the wall will hit back, and that's by how much the wall is hitting on average. Is this clear? Is this clear? Any question on this? Now, let's take another example here where we're going to look at momentum in 2 dimensions, not just 1 dimension. The example here, a soccer ball has mass of 0.4 kilograms. Initially, it's moving to the left at 20 meters per second, but then it is kicked. After the kick, it's moving at 45 degrees toward the right with a speed of 30 meters per second. Find the impulse of the net force and the average net force, assuming the collision time of 0.01 second. So if you look at the cartoon here, the ball is coming in here. Remember, in the last example, in the previous example, we said that here I can say that v1x will equal minus 20 meters per second. But I'm using v1, so I'm just only talking about the magnitude, which is the speed now. So the speed here is 20 meters per second. The speed here, it's equal 30 meters per second, and it makes an angle of 45 degrees. And this is my mass. So the mass is 0.4 kilograms. Now I look before the collision, and I call it 1. So I say v1x is equal minus 20 meters per second. But for the second case, my speed, it's equal 30 meters per second. And the angle it makes with the positive x-axis is 45 degrees. So now I'm going to take components. So the v2x now, and now I have to add x to say that I'm taking the x component here. It will be v2 cosine theta 2, which is 30 times cosine 45 degrees, and that gives you 21.2 meters per second. And v2y will equal to v2 sine theta 2, which is 30 sine 45 degrees, and this is again gives you 21.2 meters per second. You know that cosine 45 and sine 45 give you the same value. That's why you get the x component and y component here being the same. Now I know that the impulse should equal to the change in momentum, but my momentum now, it's in 2 dimensions. So I'll have a jx, which is delta px. So it is p2x minus p1x, which is m v2x minus v1x. The mass is 0.4. Your v2x is to the right, it's positive, which is 21.2. And p1x to the left, which is minus 20, and that gives you 16.5 kilometers meter per second. So that's the x component of your impulse. The y component of your impulse will be the delta py, which is p2y minus p1y, which is m times v2y minus v1y, which is 0.4 for the mass, 21.2 for p2y. p1y is equal to 0. You can say that here v1y should equal to 0 because it doesn't have y component. And this will give you 8.5 kilogram meter per second. So your impulse now as a vector, it has a 16.5 I hat, that's the x component, and 8.5 j hat, and that's the y component. Now you can get the magnitude here as well if you like. Now in the second part, they asked about the average force, and we already did this in the previous example. The average force, force should be the change in momentum over the change in time, which is basically the impulse that we calculated here divided by the change in time, 16.5 I hat plus 8.5 j hat divided by 0.01. This will give you 1,650 I hat plus 850 j hat, and of course the units are in vectors. Of course you can get the magnitude here, and you can also get the direction as well if you like. But this is to remind you that momentum is a vector. So you can deal with it in 2 dimensions. In the case of 2 dimensions, you really have to take the components, and you do the same for what? For the impulse. Is this clear? Any question on this? Now, what happens, and we'll deal with something here that we're going to call conservation of momentum, meaning that basically you have no external forces acting on the two, meaning that the summation of delta F will equal to 0, meaning that you don't have an impulse, okay, which will equal to what? Will equal to 0. So you have a situation here, 2 astronauts in space, they can push on one another. So the force FA on B, and remember, we said that the summation of the force should equal to dP by dt. So the force of A and B, now we're talking about B because there are force applied on it. And that's why we say it's the change of momentum of B, delta T. So dP B delta dt. The force of B on A, now you're looking at A, so it's dPA dt here. Now if you add these two forces together, you know that they have the same magnitude, but opposite direction, they will give you 0. And that's why you're adding here dPA dt plus dPB dt. It's equivalent to saying it is d of PA plus PB dt equal to 0. And you know a constant, if you take the differentiation of constant, gives you 0. That means PA here plus PP should be a constant. And that's where we say that the momentum of both should be constant here. That's equivalent to saying that the total momentum is constant. If the total momentum is constant, that means it's not going to change. That means the momentum before and the momentum after is going to be conserved, and this is known as conservation of momentum or momentum conservation law. But when no external forces are acting on the system, and this is a case that we have here in space, you don't have any air resistance and so on, so we're okay to say that. That's also equivalent to saying that if you take 2 ice skaters and there is no friction, the same thing applies. There will be no external forces, and you get conservation of momentum. So we say here, if the vector sum of the external forces on the system is 0, the total momentum of the system is constant, meaning that it will be what? It will be conserved. Is this clear? Is this clear? So here we talk about conservation of angular momentum. We'll take examples with conservation of angular momentum, but just to remind you again that momentum is a vector, and if you have a system, you really have to look at the total momentum of the system. So in this example here, you have mass A, which should have momentum A, mass B, which have momentum B. They give you here the magnitude of momentum A, which is 18. Remember, they don't have, it's not bold. There is no arrow on the top, meaning it's only the magnitude, 18 kilogram meters per second. Momentum B here is 24 kilometers per second. Now, that's in 2 dimensions. This is moving along the Y, this is moving along the X. So if I want to look at my mass A, it has 0 momentum in the X direction, but it has 18 kilogram meters per second in the Y. If I look at the mass B, it has an X component of 24 kilogram meter per second, but it will have 0 in the Y component. Now, I will add the X components as usual when you deal with vectors. So you take the PAX plus PPX, and you add the Y components, okay, which is PAY plus PPY. And then you can take the absolute value of the vector, and that will be the square root of px squared plus by squared, and of course that will equal to p. And you can also get a direction. So we're just reminding you here, when you have a system, you really have to take the total momenta of the components of the system, and then you can look at the conservation of momentum before and after. Is this clear? Let's take an example to illustrate this here. And the example here talks about a marksman holds a rifle of mass 3 kilogram, and we use symbol R here for the rifle, loosely so it can recoil freely. He fires a bullet of mass 5 grams. So usually you have to convert that to kilogram, and you divide that by 1,000, so it will be 0.005. Horizontally with a velocity relative to the x, where we say VBX. B here stands for bullet, at 300 meters per second. What is the recoil velocity of the rifle? And you say VRX, that means the velocity of the rifle along the x-axis, because the motion here is in 1 dimension. What are the final momentum and kinetic energy of the bullet and the rifle? So the bullet is inside the rifle before firing. There is nothing moving. So V for the rifle is 0, V for the bullet is 0. So the momentum here, it's going to equal to 0. Now, after you fire, the bullet will go this way with a speed of 300 meters per second. And of course, the rifle will recoil back. Now, if you look at external forces, we don't have external forces here. So the summation of external forces is equal to 0. And that basically comes as an action-reaction here, Newton's third law. So the momentum is conserved. The mass of our rifle is 3. kilograms. The mass of our bullet is 0.005 kilogram because we have to convert it. Before firing, the VR1x and the VB, meaning bullet 1x, should equal to 0. After firing, the V2x is 300 meters per second, but the VR2x is what we want to find out. So I'm going to say that my momentum P2x should equal to momentum P1x, but I told you that momentum P1x should equal to 0. So momentum Px will come from a system now. It is the mass of the rifle multiplied by the initial velocity of the rifle plus the mass of the bullet, the initial velocity of the bullet, but both of them are equal to 0. So this one will give me 0. But after firing, the momentum of the rifle after firing, it will be the mass multiplied by VR2x, which is what I want to find. But the momentum of the bullet will be mass of the bullet multiplied by VB2x, and that should equal to 0. You can take this to the other side here with a minus sign, and you can divide by MR. So the VR2x will equal to minus the mass of the bullet divided by the mass of the rifle multiplied by VB2x. You substitute in the mass of your bullet, which is 0.005 over 3 times 300, and that gives you minus 0.5 meters per second. So that's the recoil speed or velocity of the rifle. It will be in the opposite direction, along the negative x-axis. And you would expect that, action-reaction. Now, if we want to compare the momentum of the two, well, the momentum after the firing for the rifle, it will be the mass of the rifle, V of the rifle 2x, which is 3 times minus 0.5, and it gives you minus 1.5 kilogram meter per second. Now, if you look at the momentum of the bullet, and this will be the mass of the bullet, VB2x, which is the mass will be 0.005 because you have to convert it into kilograms. Your units of the momentum is kilogram meters per second, multiplied by 300, and it gives you 1.5 kilogram meter per second. So the magnitude of these two momenta are the same now. But if I want to look at their kinetic energies, well, kinetic energy is equal to 1/2 mv squared. So for the bullet, it will be 1/2 times 0.005 times 300 squared, and that gives you 22.5 joules. But for the rifle, it will be 1/2 times 3, that's the mass of the rifle, times minus 0.5 squared, and that gives you 0.375 joules. So there is a difference in kinetic energy, but when it comes to momentum, because we said that momentum is conserved, it's equal in magnitude but opposite in direction. And when you have a system, when you talk about momentum, you really have to if you want to compare conservation of momentum, you have to take the momentum of the system before and after. But what we did here, we looked at individual momentum after the firing. Is this clear? Any question on this one? Let's continue with that as well. We'll take another example here. And the example that we have here, you have two gliders with different masses move toward each other on a frictionless air track. After they collide, glider B has a final velocity of 2 meters per second. A, what is the final velocity of a glider A? And B, how do the changes in momentum and in velocity compare? So The masses are not given in the question, but they're given in the figure here. So mass B is 0.3 kilograms, mass A is 0.5 kilogram. The incoming speed of V B, which we call it here VB1x, is equal to minus, because it's coming to the negative x direction. VA1x is equal to 2 meters per second, moving to the right. After the collision, mass B is moving to the right with 2, and we want to figure out the velocity. B is moving with velocity 2 meters per second to the right, and we want to find out the velocity of mass A. Now we have no friction here. It's an air track. Action reaction. External force will equal to 0. That means we have a case of conservation of momentum. But we have a system. So when we look at mass A, it's 0.5 kg. The VA1x, that means 1 before the collision and x is along the x direction, it will have 2 meters per second. And after VA2x, that's what we want to find. Now, for B, the mass is 0.3 kilogram. The VB1x is minus 2 meters per second because it's coming to the left. Okay. And the VB2x is equal to meters per second. Now, we're going to look at the momentum of the system, which we call it P2x here, because it's only acting along the x direction. This should equal to the momentum of the system before the collision, and that's why we say P1. So for P2, it's MAVA2x plus MBVB2x equals MAVA1x plus MBVB1x. The mass of MA is 0.5. VA2x is what you want to find out. The mass of MB is 0.3, and the VB2x, it's going to the right with 2. Now, before 0.5 times 2 plus 0.3 times minus 2. The only thing that you don't know in this equation is the VA2x, and the VA2x will come as 1 minus 0.6 minus 0.6 over 0.5, and it gives you minus 0.4 meters per second. So now we know our velocity of mass A after the collision. Now we want to compare. You know, by Newton's third law, action reaction, if AB should equal to minus FBA. So you look at the change in momentum on B over the change in time should equal minus the change in momentum in A over the change in time. The time is the same for both of them. So the change in momentum B should equal minus the change in momentum A. So the two momenta here for the two, or the change in momentum for both A and B, one is the negative of the other. Now, if I want to look at the change in velocities, I will find out that delta VB is greater than delta VA, simply because the mass of B is less than the mass of A. So that's a case here when you can basically work it out and you start comparing different things. Is this clear? Any question on this? We have here an example, also a system, okay, and we can deal with it in 2 dimensions as well. two battling robots on a frictionless surface. Robot A with mass 20 kilogram initially moves at 2 meters per second parallel to the x-axis. So it's moving to the right, so it's positive. It collides with the robot B, which has mass 12 kilogram initially at rest. After the collision, robot A moves at 1 meters per second in a direction that makes an angle 30 degrees with its initial direction. What is the final velocity of robot B? Now, robot B here is stationary. A comes to it and hits, but after the collision, A moves this way, B moves that way. So you can look at it, it's one-dimensional before, but after it's two-dimensional. So if I look at A, MA is 20 kilograms, VA1x is 2 meters per second, and VA1y is equal to 0. For B, MB is equal to 12 kilograms. It's stationary. That means the VB1x is equal to 0. The VB1y is equal to 0. After the collision now, the A is moving this way at an angle of 30 degrees and speed of 1 meters per second. So the VA2x will equal to 1 cosine 30, and the VA2y will equal to 1 sine 30 degrees. But the VB2x, this is what I want to find, and the V2by is something that I want to find. Again, it's a frictionless surface. So you have an action-reaction. So the external forces here are going to equal to 0. So you have a conservation of momentum. So you're going to look at the momentum of your system before. That's why we say here PA1 plus PP1 equals PA2 plus PP2. So you're looking at the momentum of the system after. Now, when you do that, you have an x and y now. So you have to look at the x component first. So it is MAVA1x plus MBVB1x, and you know that it's equal to 0 for B, equals MAVA2x plus MBVB2x. So 20 times 2, that's 0. 20 times 1 cosine 30 plus 12 VB2x. And the VB2x here comes as 1.89 meters per second. So you calculate the x component of the velocity of B after the collision. You do the same thing for the y. MAVA1y plus MBVB1y should equal to MAVA2y plus MBVB2y. Now, the A initially has no y component, so it's 0. The B, it's not moving, and it has 0. So you look at it after the collision, it's 20 times 1 sine 30 plus 12 VB2y. So the only thing you don't know here is the B2y, and we get the B2by here as equal to minus 0.83 meters per second. So you can write now here your velocity as 1.89 I hat plus, well, it's not a plus, it's a minus 0.83 J hat meters per second. So that now is your, and this is here has to be VB. Okay. 2 after the collision. Now, you can get the magnitude, you know how to do that. And you can also get your direction, beta here. And beta is equal to tan inverse of the y component over the x component, and it gives you minus 24 degrees. That means it's below the x-axis. Now, if you want to do it relative to the positive x-axis, as we did in chapter number 1, you know that you have to add to this 360 degrees, and that will give you 336 degrees relative to the positive x-axis, if you want to do that. But you can say that beta here is equal 24 degrees, and that's enough. So you can say here beta is equal 24 degrees if you just want to state what's in the figure here. Is this clear? Any question on this? Now, let's take a few questions here to test or to argue on what we did today. Question 1, you are testing a new car using crash test dummies. Consider 2 ways to slow the car from 90 kilometers per hour, and for the American, this is 56 miles per hour, to a complete stop. So you want to go from 90 to 0. They give you 2 situations. You let the car slam into the wall, bringing it to a sudden stop, and you let the car plow into a giant tub of gelatin so that it comes to a gradual halt. It will do it slowly. In which case is there a greater impulse of the net force on the car? Now, by definition, we said that the impulse is equal to the change in momentum. So in this case, it is one-dimensional, so we can say that Jx will equal to delta Px here. And you want to go from P2x minus P1x, okay. And you know that the P2 should equal to 0, but you're also going to have a minus sign here, so it will give you a plus, but you have an impulse. In both of these cases, by the way, you will get the same thing because you're going from V 90 kilometers per hour to V is equal to 0. And that's why we say here the right answer is C. The impulse is the same in both cases. But remember, what is going to be different is going to be the average force. The average force will going to be the impulse divided by delta T. So in the first case, your delta T is going to be small. So the average force is going to be big. In the second case, your delta T is going to be smaller. And that means the average force will be less. And that's why in a car, you have airbags. The airbags will give you a gradual, when you hit, it will give you a gradual halt. And that will have less average force on you, and that will be less damaging. And that's why we have these airbags in cars. But if there is no airbag, the stop will be sudden and the average force will be greater. And of course, that will cause what? Will cause damage. Any question on this one? But in this case, we say the impulse is the same. But if I ask about the average force, no, then it will be different. Okay. This question here is related to what we did in the example of the rifle. 3 kilogram rifle fires a 0.05 kilogram bullet at a speed of 300 meters per second. Which force is greater in magnitude? The force the rifle exerts on the bullet, or the force the bullet exerts on the rifle? And they give you options here. You can look and you tell me what is the right option here. You know that this is a case of total external force is equal to 0. So you have action reaction here. And when you have action reaction, you know that the two forces are going to be equal in magnitude, but are opposite in direction. You're right. It is what it is. C. Both forces have the same magnitude. And this is now just to try to test what we learned. So in summary here, we define momentum, and we said that momentum is related to mass and velocity, and we said it's equal to mv, and that enabled us to write in Newton's second law in a different form. We know that it is equal to ma. We can also write it as dp by dt. And we define impulse, and we said the impulse is the integral of the force over the time interval. But you can also say if the force is constant, then J will equal the force multiplied by delta T. And in some cases, you can regard this as an average force, and you can always look at the average force if you know the impact time or the contact time on the object. So this is one thing we did. And for an isolated system, we said that our momentum before and after is conserved. In some textbooks, you may actually see P initial should equal to P final. And this is basically what we dealt with today. Is this clear? Any question on these? Any questions on these? All right then.